Um,
It's fine.
Not here. Can everyone hear okay? Is this Kifan or Tengyu?
It's me, Tengyu.
Okay, yeah, I think we can hear you well.
Okay.
And you can
Okay,
control
thanks.
the slides, right?
Yeah, I'll change this. I couldn't hear you very well, but I guess you can hear me, right?
Yeah, we can hear you.
Okay, sounds
All right,
good.
so it's great to have Tengyu join us remotely to talk about LLM theorem provers. Yeah, go ahead, Tengyu.
Yeah, thanks so much. Yeah, I'm sorry that just I had a flu or maybe some kind of cold just last minute. Just I guess you see I'm drinking a lot of water and having some running nose. I cut my slides a little bit as well just to make it easier with this. Yeah, I was actually looking forward to going back to some of the conferences in academia. Anyway, so this is the work that I've done with my student Kefan. On theorem proving. So actually the most of the approach is pretty empirical. I guess the goal is to prove theorems. So I guess that's count as some kind of have some relationship with math. So I thought it's probably fun to talk about it in this context. So I guess the main motivation is that it sounds like reasoning capability seems to be in some sense the only barrier between us and AGI now. Like the models are very good at grasping knowledge, but the reasoning is not perfect yet. So and for now, let's say reasoning is really coding plus math. I think that's kind of what the community is focusing on. Of course, there are reasoning in physics, in STEM, so on and so forth. So I guess you can think of this as either generating code or maybe solving math problems or proving theorems. And we're going to focus on proving theorems. I guess when I talk about this to other people, especially mathematicians, I think it seems to be the common concern is that can really large language model understand mathematics? Do you really believe that they can do Riemann hypothesis of P versus NP? Oh, P versus NP, not N versus NP. Sorry. So but I think the argument here is that I kind of like believe that large language model can do this. At a certain point, how long it takes, I don't know, because I don't know how difficult Riemann hypothesis is. And the reason seems to be that personally for me is that first of all, the classical search-based ultimate theorem proving approach actually really doesn't understand. So they understand even much less than the current large language models, if you think about it, because they are just searching, right? So you are just try all kind of like different proof strategies and see whether they work out. So they are really just machines, right? So they don't have any intuitions, they are just very mechanical. So the large language models actually are much more similar to how humans learn and behave. So I guess I'm listing a few things here, right? So human mathematicians relies on intuitions, right? So from few short examples or from many examples, right? So the human mathematicians actually do pattern matching sometimes. At least when I try to prove theorems, sometimes I just try to pattern match a little bit. So and there are imaginations and hallucinations. You can say this is good or bad. Hallucination of course is bad, but sometimes it's not very far from imagination. And these days for DeepSeek R1 and O1, so on and so forth, it's kind of like observed that the models can actually have some self-reflection and self-correction. And also, interestingly, even the incapabilities are very similar. So humans are actually not very good at doing very long, precise mechanical deductions. Of course, mathematicians can be trained to do that reasonably well. But I think, at least, it's not like mathematicians are expected to multiply two 9-digit numbers very fast, right? So I think the crust or the real innovation doesn't come from the mechanical deductions, but more come from the intuitions, the understanding, so on and so forth. So, and my kind of like probably overambitious argument here is that so artificial neural networks seems to be very good at simulating biological networks so far for many different tasks, especially on how they learn from experiences or data, right? So learning from experiences, right, in some sense, it's kind of like how you get intuitions from seeing so many mathematical theorems and proofs, and you cannot really exactly articulate how does intuition comes, right? You have to say, oh, I just feel this is right? So because I've seen so many theorems, I've successfully proved so many theorems, this is feel the right direction. And another thing is that, if you think about large language model today, I think at least large language model today for theorem proving is definitely better than humans in 1500s. For sure, I think that's just almost kind of like a consensus, right? So it's probably at college level right now. So and at least even last year, I think it's better than 1500s. And if you think about 2025, with all the O1 and the R1, I think most of the large language models can do better than what people did in 1700. So so basically humans are not kind of like at human level, just like a randomly just from day one, right? So humans actually keep improving themselves, by learning from the data they generated themselves. So so I think I'm kind of like optimistic on how fast large language models can learn mathematics. And it's not like large language models are given less data than humans, right? So in 1500, I don't think in 1500 there were a lot of mathematical books, right? So lack of data shouldn't be a problem for humans. Lack of data was not a problem for humans in 1500, and it shouldn't be a problem for large language models in 2025. Okay, so and I guess we're focusing on this talk is going to focus on formal theorem proving, and the main reason is just that when you are writing in formal language, you have the formal verifiers. So and these verifiers can reliably test the correctness of the formal proof. You don't have to think too much about the reward hacking. You can have an objective evaluation, and also it doesn't really have any ambiguities from the natural language. It's very precise, and also you don't have to know all the natural language kind of like, you don't have to know what's the best restaurant in Italy, right? So you just have to understand this particular language, either Lin or Isabel, which are the most common ones. And because of this, you can, at least it sounds like people are doing very meaningful research with 7 billion parameter models with a few billion training tokens. We can see pretty good results, and that's more amenable to academia in some sense. I think the caveat is the large language model, the formal provers are weaker than natural language provers, but part of the reason is just the models are smaller, right? So, GPT-4, O1 has much more parameters than the 7B models people release open source. And also it just takes some time for the open source models to catch up, I think, in some sense. But I do feel like the open source models can catch up, especially if we just narrowly focus on the formal theorem proving, but not anything else. So just to give you a rough sense on how the formal language works, it's pretty much just a way to formally write the language so there's no ambiguity, right? So it can express pretty complex ideas and theorems, in relatively succinct language. And in most cases, the formal language are designed so that they are imitating natural language. They are just making things formal. So and the space, so maybe just a quick overview of this space. So I think there are probably few benchmarks, 3 or 4, and 3 benchmarks. These are mini F2F, ProofNet, and Putman bench. So these are evaluation benchmarks which has a collection of theorems that that are exactly correct. So the mini to F2F is more on the high school level, ProofNet is more on the college level, and Putman bench, as the name suggests, they are formal statements from the Putman computation. And there are a bunch of prior works. I think mostly Theorem Llama, DeepSeek Prover. I think that it's called DeepSeek Prover 1.5 technically, and Alpha Proof, which is by Google. And most of these are using RL, and sometimes they leverage some natural language statements by formalizing that natural language statements into formal statements, so you get more training data. And there's another line of research which tries to use tree search-based methods together with large language model. I think that in some sense that's a little bit more orthogonal, because once you have large language model, you can still always use tree search to augment it. So that's not quite the comparison set for this talk. And the training data sets, I think the main thing are just there are some proof libraries that people wrote when they developed the previous generation of the automated theorem proving techniques. So MATLAB4, AFP are some of this. I think AFP has probably 100K theorem statements, or maybe more than that. And Lean Workbook is also on that scale, but Lean Workbook is automatically translated from some of the context level theorems in, I think, in its AOFP, Art of theorem problem solving, something like that. So and the issue with Lean workbook is that it's not guaranteed that all the theorems there in formal language are correct or provable. So actually, just the last 2 days, I think some of my students actually manually labeled some of the randomly like 20-30% of the statements in Lean workbook. I think 50% of them are correct and provable. And it does require some time to check each one of them. You have to prove some inequalities, to make sure it's correct or not. So okay, so the prior work is using RL. I guess maybe let's just quickly review that. I guess you'll probably all have seen DeepSeek R1. So basically, it's kind of a way to, of course, the exact algorithm here I'm talking about is not from R1 because those are for more general purpose, but it's the same algorithm if you apply it to formal theorem proving. So basically, you have a prover, right? So which tries to generate proofs, right? So you have a bunch of statements, they are given to you, and there are no proofs. So you just try to prove them, and then you verify with the Lean verifier or the Isabelle verifier, and then once it's correct, then you say the correct ones have reward 1, and then you retrain the model with the correct ones, the correct proofs and statement pairs. So so basically, sometimes people call it, I think in this area people call it expert iteration, but it's actually really just reinforcement learning with binary reward. It's the most vanilla reinforcement learning that you can imagine. So I think the challenge, here, like we try some of these methods, and the improvement over time, I didn't have that slide. So basically, people found that as you train longer and longer, the return becomes log-in linear. I think this is also reported by OpenAI in their blog post. Generally, the training and inference time kind of curve, becomes log-in linear in some sense. So I think in my opinion, the problem seems to be that just you cannot believe that we have enough advanced theorem statements for us to run RL to generate to other open problems, right? So the more challenging the problems are, the fewer the problems are, right? So you probably have like maybe 1,000, maybe 10,000 advanced theorem statements, and that's probably not enough for us to generate to other open questions. And eventually, at some level, we just don't have enough theorem statements. For example, on the Riemann hypothesis level, there's only one statement there, probably maybe 10, and there's not enough kind of like theorems to learn. So in some sense, I think the RL performance seems to be bounded by the difficulty level of the existing data sets, not the proofs, because these data sets don't have proofs; they only have the theorem statements. But the theorem statements difficulty level seems to bound the fundamental capability of the models you learn from them. So and another technical reason is that, which is kind of related, is that because some of these theorems becomes harder, some of the theorems are very hard to prove. So it's very difficult to find correct proofs, and then that slows the training process. So I think one of the paper estimate that 98% of the compute is wasted on unsuccessful proving attempts. So basically, you just have zero reward for 98.5% of the cases. So I think maybe all of this seems to be kind of challenges and seems to kind of contradict with my view here. And I was thinking about this. I wonder why I was wondering why large language models cannot do as well as humans. Humans are not trained on a lot of data either, right? So and I think my reflection was that actually the mathematicians are not just running RL. Right, that's probably part of it, right? So you do try different theorems, and you try and once you prove it, you try to understand it better, and you publish it, and everyone else understand it better. So that's kind of like RL. So right, you try and error, right? But there are many other ways to develop mathematics, right? So I think one of the ways I'm thinking about is we are thinking about in this paper is the conjecturing, right? So it's not like there's a fixed number of theorems there in this world, and actually many mathematicians develop mathematics by conjecturing new theorems and setting out new agendas. So sometimes I think people even say once you find out the right conjecture, the right formulation of the theorem statement, that's already kind of half done. So I think I think in some sense, I think the RO algorithm probably are not really simulating how mathematicians are learning from the mathematicians learning themselves. So because of this, or because of many other reasons, so just because mathematicians are not just only running RO algorithms. So that's why in this paper we are trying to take some inspirations from how mathematicians develop theorems. So or mathematics. So basically, we try to kind of like the models practice on variants or extensions of known theorems, and also propose and prove conjectures. So basically, you either propose some variants of the existing theorems or some conjectures, and then you try to prove them. So basically, it's a self-play algorithm where the conjecturer tries to say that, given a theorem statement X, let me generate some extension, a conjecture Y. Right? This could be a harder version of X, or it could be a variant of X, or it could be something related to X. And then the prover tries to prove the conjecture Y, and you do this iteratively. So this will generate infinite number of kind of like theorem statements or conjectures, so that you never have this issue that you exhaust all the existing statements. So I guess just for some terminology, I think conjectures in this talk will refer to those generated statements or conjectures, and the statements are, this is just my terminology for this talk. Statements means that those statements are given from existing data sets, and conjectures are generated by the large language models. So, and you can see these are some of the examples for the generated conjectures. So what we do is that we start from this statement X, and we generate some related ones. So, so these are real examples we pick from the model. So, so example 1, you have this, 1 plus x squared is less than 1 plus x squared, and then the general conjectures actually are quite similar, but just changing the variable x, changing the x squared by x to the power n. So, and the same thing for example 2. So these are relatively simpler ones, but I think we don't really go beyond this that much. Most of the general conjectures are like this. They are probably a small fraction of the cases which are a little bit more insightful, but most of the cases is like some variance. So, and the algorithm, as you can imagine, which is I already kind of almost talk about, it's basically just that you first conjecture, and then you try to prove, and then you verify, and then I guess some of the details I'm gonna skip. So, and after you verify, I think the question is that how do you keep training the conjecturer and the prover, right? That's how you reinforce the correct behaviors. So for the prover, it's the same thing, right? So if you have successfully proved any conjectures, because if you have successfully proved any conjectures, all existing statements, then that's a success. That's reward 1, and then you just retrain with that statement or conjecture and proof pair, right? So that's how we train provers, which is the same as before. And the question is more about how to train the conjecturers. So and so basically, what's the reward function, right? What kind of conjectures you want the conjecturer to generate? So so we want to generate elegant, approachable, and challenging conjectures, because if it's too trivial, then they are not very useful. If they are too hard, then you cannot prove them, then they are not useful. And they have to be somewhat elegant, as opposed to some kind of like very messy, lengthy statement, which is not very insightful at all, and that's not very useful. So basically, we design some ad hoc kind of filters for the elegancy filter, which I'm going to talk about later. And also we say that if the conjectures are proved 1 to 8 times among 32 trials. So 32 examples here means 32 trials from the prover. So the provers try 32 times, and if you get a non-zero success rate and also less than 25%, 8 out of 32, right? So then you say this is a good conjecture. It's not too hard, not too easy, and we know it's correct because it's proved once at least. So that's how you get the right conjecture. And then given the right conjecture, we just reinforce generating that conjecture. We just train with the statement, proof, and conjecture couple, right, to reinforce the conjectures to do these kind of behaviors. So and there are some subtleties here. I think I have probably 20 minutes, 15 minutes. So, and there are some of the technical details here to make the performance really better. So, so one of the challenge we have is that the conjectures sometimes just lose their diversity. For example, one of the very typical cases is that the conjectures just keep generating inequalities, right? Even given a seed theorem, which is about number theory. So I guess this is the third bullet here, right? So you give a theorem, P is a prime, P can divide A squared implies P can divide A. So that's a number theory statement, and you expect the conjecturers to generate something related in number theory, but then the conjectures have a mode collapse and just always generate inequalities, and then it generates something like this: p the prime, then p squared is larger than 4. And maybe it's actually generating something much more complicated than this. Maybe p plus 3 squared over 5 times p cube is bigger than 3.5, which is still a correct statement, but it's not about number theory. It's really about inequalities. So I've seen this a lot. So the fix to this is that we try to, maybe I'm just quickly show all of this. So we try to have something like try to preserve diversity. This is again some kind of like ad hoc approach. It would be nice to have some theoretical study on what's the right principal approach to do this. So so the ad hoc approach here is that we try to reweight the general conjectures. So basically you have a bunch of like unproved statement in the existing assessed Lean workbook. So you have, for example, like 3 statements which is about inequality and 3 statements which is about number theory at the bottom in the red color. And then when you generate conjectures, probably generate 4 statements about inequality and 1 statement about number theory. And you want to reweight the distribution a little bit. So what we do is we do some kind of faster than distance matching so that you weight up the number theory statement you generated, the number theory conjectures you generate by a factor of 3, and you downweight some of the other inequalities you generated. And then you kind of keep trying to encourage the conjecturers to generate number theory statements. Anyway, this is a relatively kind of like ad hoc approach. And this is what I refer to about the elegancy score, which is also another very important tool. So we define elegancy by the length of the shortest correct proof divided by the length of the conjecture. So basically, the shorter the proof is, the better, the more elegant. The shorter the statement is, the conjecture is, the more elegant. You don't want very lengthy conjecture, which has a like 1-line proof, right? So basically, the longer the proof is and the shorter the conjecture is, we define to be more elegant. Of course, this is again a heuristic. And we just remove conjectures with lowest 20% of elegancy score. Yeah, and this is very useful. Each of these components, we did some ablation study, and this is very useful because otherwise you just generate these very, very like long conjectures, like maybe sometimes like 10 lines, and then the proof is really just that one statement or 1 line. And we have a bunch of other technical details here, just in case you are interested in, but maybe I'll skip this just in the interest of time. So we also, for example, try to make sure the proof is shorter, right? That's also another way to counterbalance this, right? So here it sounds like you are encouraging longer proofs, right? So because of this, but actually there's also another component in the prover, in the discount factor of the prover, which tries to penalize the length of the proof. And also we start with the DeepSeek prover V1.5, and we keep training with our algorithm or with the same our algorithm, and we can see we are much faster than that. So basically, that's the left bottom figure is what we did, right? So the starting point is the DeepSeek prover, and basically you can view this blue line as keep training the DeepSeek prover using the same algorithm, right? So like for longer and longer. And the right line STP is ours, and you can see that it's improving much faster to a much higher accuracy. So I guess we start with something like about 15, and we reached to 26, and now the newest number I got is probably 30%. And we estimate that totally there are 50% of correct statements. So we are not that far away from the best we can do. Like the base optimal is 50% just because half of the statements are incorrect. So and you can also do this thing at any different checkpoints where you can try the standard expert iteration, which is just RL, and you can try our method, and at any checkpoints our methods has better scaling compared to RL and parallel sampling. Parallel sampling I didn't explain. This is just you keep sample from the existing model without any retraining. It's just best of n accuracy. And we also test on so these are on the training side of the Lean workbook. So we get the best number of statement proved on Lean workbook. I think the previous batch was 13%, and then and now we got to 30%. So and we also try this for after we train on the Lean workbook. So we also test on a few of these data sets I introduced, MeF2F, ProofNet, Putman Bench, and we get the best on all of them. So And I guess maybe I'll skip this. So this is just an example of some of the conjectures we generate and the proofs for the conjectures. So they're not that entirely trivial. I guess in this case, the conjecture is something about inequality n is bigger than 1, then 3 to the power of n plus 1 is bigger than 4 times square root 2 to the power of n minus 1. And then the rest of them is the proof. So, and these are some more readable kind of like statements we generated. We proved in Lean workbook, so that you get a sense on how difficult the questions are. So, so there's some inequalities statement here, like which is kind of like those kind of IMO kind of like questions, maybe slightly easier than IMO. There are questions about number theory. There are questions about, I think question 3 is pretty simple. It's probably just the AIME kind of level, and question 4 is more like a functional analysis kind of things. Yeah. And we also have done a bunch of ablation studies where we found that the success rate for proving the conjectures is much higher than the success rate for proving the statements in the given data set. And that's just because the conjectures, some of them are easier, some of them are variants of the existing theorems. So that they gave a much more training signal, because now you can find successful proofs, as opposed to for the existing data sets, often after a while, then you cannot find any successful proofs, and then you get stuck there. Yeah, I guess that's all what I have. Some of the future work, I guess one of the challenge seems to be that the formal theorem provers' performance is still less than the natural language theorem provers. As I said, probably one main reason is that the natural language theorem provers is ChatGPT, right? For 03, right? So ChatGPT 03 mini, right? So but I still believe that if we do some kind of translation and leverage natural language data, then the small formal provers can get to similar performance as the very large natural language provers. And there are some perspective about efficiencies, for example, how to incorporate the error message from the verifier. Actually, the verifier does a lot of work under the hood. It actually keeps track of many of the so-called verifier states, which are the intermediate steps in the proofs. And those intermediate steps are often very insightful. So if you give them back to the model, it actually helps the performance. I think some people have been trying this with O1 or R1. And another thing is just that maybe formal theorem proving can also generalize to other tasks, maybe physics, maybe some other coding tasks. Hopefully that some of these reasoning tasks are transferable to some degree. The reasoning capabilities are transferable, but that's kind of like a long-term question. Thanks. I cannot hear, so yeah.
All right, thanks so much. Thank you for joining remotely.